Okay, I very quickly wanted to talk about similar figures and go more into definition of what similar figures are. So these two triangles right here are similar to each other. Okay, and when you see somebody say these are similar figures or these two triangles are similar to each other, it means wow, I can't count. It means four things. The first thing, it means that they're the same shape. Okay, a trapezoid is not similar to a triangle. A circle is not similar to a square. Okay, and so when we talk about similar figures, first and foremost, they are the same shape. Second thing, they are different sizes. Okay, one's big and one's small, and a lot of times that's how I label mine, as big and small. Okay, thirdly, they have corresponding sides, and these corresponding sides are because they have the same ratio. Okay, so there's a ratio between shapes, and there's also a ratio, oops, can't write, a ratio between these sides. Okay, and so I'm going to kind of show you those as well. And then they have congruent angles. Okay, another way that we can say congruent angles is we can say the word same or equal. Okay, and so what I mean, we'll kind of go through all of these. Okay, so same shape, check, that's easy. Different sizes, check. The hard ones are the corresponding sides and the congruent angles. Okay, so let's start with angles first. One thing that I always have my students do, and I would like for you guys to do, is to stack the name of your shape. Okay, and if it gives you the description up there, that's the order that you write it in, and that's how you're matching up sides. Okay, because a lot of times they can rotate it, they can flip it, they can reflect one of these images. And if it's not a triangle or a shape that's easy to pair up your corresponding sides, it can mess you up. And then therefore your ratios and your corresponding angles and corresponding sides can get messed up. And then therefore you don't have that relationship that you were looking for. Okay, so what this is telling me, we've talked about this before, is with my angles. Okay, so angle A right here goes with angle D. That's the beauty of stacking these names. Angle B is going to be the same measurement as angle E. And angle C will be the same as angle F. Okay, and so if I just throw some numbers in there, whatever that they were going to be, if I said that A was a 30-degree angle, then automatically I can know, because I know the properties of similar figures and I know the relationship of similar figures, then that is also 30 degrees. Okay, and so that's what is nice about that, because sometimes they'll have sides missing, and we have to be able to look at these and know that relationship to kind of fill in those blanks. And so that's an important one. Okay, another important one is your sides. Okay, and this is where having this stacked really helps us. So side AB is similar to side, well, AB is here, DE is right underneath of it. So side DE. Side BC is similar to side EF. And then I just keep moving left to right. And so to get that last one, I kind of circle, I make a loop back around. So then CA, side CA, is similar or corresponds with side FD. Okay, and that's how I have it color coded. So if I go back in here and I color code this, so CA was here, and there's my FD. My BC is here, And I'm just checking in the figure because obviously I want to make sure that the figure is correct and that I didn't mess up, and that looks great too. And wrong color. And then my pinks are right there. Okay, and so we're able to see that. We're able to see that relationship. We're able to see the corresponding sides. Now, if I take it a step further and we talk about relationships between the two figures. So if I have old, scale factor, new, which is our proportion table that we use to find missing sides of things that are in a proportional relationship. So I'm going to have green over yellow, green over yellow. So I'm going to start with the big one because the big one has both sides. This one is the one that is missing. Okay, and whatever shape has a side missing, that's going to go here because it makes it a lot easier for us to solve if we can move left or right. Okay, which is very natural for us in math problem solving. Okay, so green over here is 12 over 8. And then this over here is going to be the letter K, our unknown, our variable, over 6. Okay, and so what we want to do is we want to find this relationship of moving left or right. So 8 times what equals 6? Well, that one's not an easy one, but it's okay because we know to get scale factor, we can do new over original. So 6 over 8, and I'm just going to simplify this by 2. And so I'm going to get 3/4. Okay, and so this right here is my scale factor. Okay, one thing that I noticed is that 3/4 is smaller than 1. So as I'm moving from this shape to this shape, it did get smaller. And I like when those things match up. All right, so times 3/4. Okay, and you should have your pen and paper. You should be working on a scratch piece of paper. And so pulling this down and working it below should not be that big of a deal. Now, when I do times 3/4 and I do 12, it would make my life a lot easier if I throw that baby over 1. Because it's a whole number, when I represent that whole number as a fraction, I throw it over 1, or I can put it over 1. I say throw it to make it fancy, but I'm putting it over 1. All right. So you can early reduce if you would like to early reduce, or you can just multiply across, whatever works best for you. So if I multiply across, I'm doing 12 times 3, which is 36. And then I'm doing 1 times 4, which is 4. And then at this point, when I look at that, I see 36 divided by 4, which then we can run to our calculator and put that in, or maybe you already know it off the top of your head, and what you should get is 9. So my missing side is 9 units long. Okay. And so when I'm looking at this, I talked about that there's some ratio relationships in there. So if I pull my big shape, okay, what we had was 12 over 8. And if I simplify this, there's a common factor of 4. Then I can get 3 halves. Okay, so this is the ratio within the shape itself. Okay, the 3/4 was the ratio between the two shapes. Okay, so this was from shape to shape. Okay, this ratio that I just found right here is from side to side within the same shape. Okay, so if these are truly corresponding, similar figures, then that ratio that I just got right there will be the same one in the small shape when I compare the green to the yellow. So we now know in the small shape that the green side is 9 and the yellow side is 6. And I can simplify this by what? 3. So 9 divided by 3 is 3. 6 divided by 3 is 2. And by golly, if you don't look at that, okay, these two things, these two ratios that we just found right there, they don't have to be. Sometimes they probably could be. That'd be really cool. Have to be the same ratio as this one here. But notice that we're comparing two things from shape to shape. So big to smaller, small to big. And then this one, I'm comparing the green side to the yellow side. So I'm comparing the sides within each individual shape But because they are similar figures, they have the same ratio. Okay, and that is what I was talking about earlier with that relationship. Okay, so hopefully this helps, kind of breaks down our similar figures again. I just did that so that you guys remember what a similar figure is. The questions that you're going to see over similar figures are going to be about missing sides. Okay, and so you're going to be doing something like this, not so much breaking down the other stuff, but I wanted you to see where that relationship came from.